this video, and this is the continuation of the 32-bit processor. And today we are discussing the fifth module in the series, that is control unit. So today we are going to discuss the code of the control unit, the test bench code of it, and the various diagrams or the steps in implementing it on the hardwares, the steps before implementing on the hardware. Right. So let's first see the diagram. So today we are going to make this section. So here you can see there is one input that is coming from the mux to here. And this is the branch, this is memory read, this is memory to reg, and this LU operation that is uh, coming out of the control unit and coming into the ALU control. And this is ALU source that is coming into the mux. And this is the rag right? And this is the instruction set. So these are the things. Now let's see the code. So we define the module first, and the input as opcode. Why we define 5 is to 0 here? Because the opcode is 6-bit wide, right? And we define it as wire because it represents it as physical wire, and this wire and rag are the data types here, and the output and are as follows. So why we uh, define the ALU operation, the ALU op as 1 is to 0 because it's a 2-bit signal, right? Then we have always block. And why we use this is a combinational always block. And why we use star here, because this will enables, not enables, but this is uh, we use in order to, like, if the input is added later, so the code automatically include them in the this sensitivity list. So why we include the star here, because whenever the input changes, this particular always block is executed. So instead of mentioning each input here, suppose we have n number of inputs, so we are not going to mention each of them in the brackets. Rather, we use this star symbol, the asterisk symbol, right? uh, in our project program we can write opcode here, but it is very good practice to use the star in this block, right? So it will be better from the coding perspective. Now let's see, we begin, and then again we apply the switch case. It will work as a switch case, but here we called it as a case, right? So in that we provide the opcode because this is the only input that we have, and then after we make the cases. So this is the case one in which we are providing in the 6-bit 0000 value, right? And why we are making cases? We are making four cases here. The first one is the R type instruction case. So this is the R type instruction case. So here we are assigning 00 in 6 bits, and now we are assigning the reg DST is equals to 1. So this result is going into the RD, and branch is 0 here. That means no branching. Then memory read is also 0. That means no memory used. And then memory to reg is 0. That means write ALU output. Then ALU output, memory is first the memory to reg is 0, so memory is not used. Then write ALU output. So ALU output operation में हम दे रहे 10 value. This 10 value is sent to the ALU control, right? Then ALU will use this, and we assign the memory write as 0. So we don't write into the memory in this case, right? And we are also assigning the ALU source as 0, and we take the second ALU input as 1, and this is stored in the ALU result. Now let's discuss the second case. Second case, we are providing some value here other than the 0, and in this case we are doing the load word operation, right? So first we make the memory read as 1 because the data is now read. Then memory to reg is 1. The memory data goes into this register, and the ALU source is 1. Since immediate offset is used, so now and rest values are as same, and we assign the ALU op as 0 0. Now the third case. Since third case we also change the value, and this third case is the store word case. Memory becomes 1, register becomes 0 because nothing is written into the register. It's a store word. We are not writing anything in this case. Now the fourth and the last case. So this is the branch if equal case. So we assign the branch as 1 because the processor can be jump in, right? So ALU operation, we assign it as 0 1. ALU perform the subtraction for comparison. So for comparison the code is 0 1. Now we make the rest of the values according to the first case, and then we set the default case here as 0 0 to all values, right? So processor should not generate a random output if we assign the default case value. Then we end the case. Now let's see why we make all these four cases. These are the not random four cases because in this way we check the ALU operation or control unit operation. So, for example, if our first case we assigned the opcode as 0 0 0, so it will the control unit will understand that this is the R type instruction. Then it will generate a specific combination of the control signal so that ALU performs the required operation, and the result it will written back into the register. Then we have the second case. So in this case, the processor understand that the need to read the data. This is the read case, right? So in this we only read the data. That's why we assign the read operation as 1 1, right? We're not storing anything in this case. Then in the next case, we're storing. In the third case, we're storing the values. That's why we assign here the memory write and this ALU source as 1, right? And then in the last fourth case, what we are doing, we are branch if equals to. We are doing comparison. So for comparison, we are assigning the branch as 1, and this is default case. So this is about the source code. Let's discuss the test bench. So here test bench is for that we create for testing whether our source code is working well or not, and is there any probability of error when we implement it on the hardware. So before implementing it on hardware, we are testing it here in the app itself by creating the test benches. So if we create the module name can be something related to the source code. It will be a great practice if you do so. And then we assign the rag as 5 is to 0 opcode. This is the input. Previously we assigned it as via data type, but now in the test bench we make it rag because we are providing the input, right? And these are the wires. output begins wires. This is not the case in this is not the case in every situation or in every module we'll see, but this is the requirement of this particular module. That's why we are making the rag and wire data type as follows. And now we are making the instance of the control unit module. So for that we have to name an instance of the module. That name can be anything. This is a general practice that people are using UTT, but you can use anything as a instantiated object name. And we are making this a port mapping with the dot operator. So this is a syntax how we can make the port mapping. So, what is the port mapping? We are connecting this test bench input and output to the to the control unit. Okay. So, in this way, we have to include every output and input that we write here in this format, in this instantiated. And what is instantiated module? We are creating a copy of it so that we can test on it or we can use it. Then initialize begin, we write here, and in after the initialize begin we're writing those values that we are going to test. So we are taking inputs only, and here is the opcode. First we assign it as 000, and after 10 nanosecond this hash 10 is the unit time, a time unit space. We are taking in nanosecond. So after 10 nanosecond, the result is changing in the simulation or the signal part. So we are assigning different values according to the case that we assign. So and then finish. So this finish will tell you that now this thing, initial begin block is now end, and then end the module. Now let's see the simulation. As I told you earlier that if you have multiple modules in your source section, then you have to perform the simulation and other operations. So for that you need to click on that, right click on that and set as the top module. Since it is already top, it is now a bit bold and differentiating in nature. These I already set it as top. So you have to do this for both the design sources module and the simulation source where your text file is. So you will have to make all uh, the module that you're testing as the top, to set as the top. Now let's click on this test bench and click on the run simulation, and you have to choose behavioral simulation. And after some time your simulation part will see. If you don't see in the name column these objects, so you can just drag and drop here, right, in this way. Like I will show you this, like in this way. If you don't see any, because I already set up this thing so I can easily see the values. Now you will check that this opcode is changing or not properly. We are providing four test cases, four values, so these values are correct. And you can also check the values according to your test or switch case, right? For my case, these values are correct. And now let's see the RTL schematic diagram. So these are the steps when you are planning to implement it on the hardware. So you have to repeat all the step one by one, from coding module to simulation, running simulation, and then RTL schematic, then synthesis. So these are the flow. These are the flow. These are the flow of implementing. So you can see the flow navigator box and go step by step. So this is the diagram, schematic diagram of this control unit. You can see it clearly how the connections are made. Now let's run the synthesis. So after running this synthesis, you will see a very detailed schematic of this control unit with the gates, logic gates. It will take a little time to run. I will show you that this, if you click on here, let's first open this. So now you will see that when I open the synthesis, uh, then we have a device, a full device file here in which you can see the whole chip. This chip contains multiple blocks, right? And you can see this highlighted yellow dots. That means your code is working well, and you will see the connection here. You can click here, right? I already clicked, so I just double click on that. If you zoom it, we'll see the connections. In this way, the things are going inside the chip. We'll see how fine and intricate the designing of the chip is. It will only show these dots when your code is working well and all the process are executing in a well manner. And you will see in the net list the control unit, the nets and the leaf cells. So if you get these things here, that means you are going in the right direction. Then you can see the schematic. This is more a detailed schematic of the ALU. As I told you, you will see the logic gates here, right? You can also run the implementation, and if you are working on hardware, you can also generate the bit stream. I'm not doing that, but you can also check by running these both options. We will explore more options as the time passes, and you will also learn it by yourself how to explore this tool. This is such an amazing tool to learn the hardware coding, right? So that's it for today's video. I hope you have cleared all your doubts regarding the previous value videos and values of rag and wire. And we will see you in the next video, and that is about the sign extend module. That's it for today. Thank you guys.